Hello everyone, and welcome to a second example of quantitative energy bar graphs. In this one we have a 20 kilogram box pulled from rest, and it's going to be pulled 5 meters across the floor, dragged if you will across the floor, by a 300 Newton applied force. So I'm going to take you through a few steps here to get some of the basics out of the way, and then eventually we'll apply energy to this situation. But let's start out by drawing a force diagram of the box. So there's the box. The forces that act are, of course, the force of gravity exerted by the Earth down on the box. The surface is supporting the box, that's upward. As those are the only two vertical forces, we then have the applied force to the right, and we have to assume here that there is a frictional force to the left. Now, a couple of things. You will notice here that we're not sure how much friction there is, but we can assume that there's less than the applied force. Why does there have to be less? Because the box is starting from rest, and the only way it could move 5 meters starting from rest is if it was accelerated, and therefore f of a must be bigger than f of fk. Now f of n has to balance out f of g because it's not accelerating up and down. F of g is, of course, mg, where m is mass and g is not gravity. F of g is gravity. G is the gravitational field strength. Plug in the mass, and assuming we're on Earth, a gravitational field strength of 9.8 newtons per kilogram, and we get a normal force of 2.0 times 10 to the second newtons to 2 sig figs, or 196 newtons, which is what we're going to use later on. Part B. Now that we know the normal force, let's figure out how much energy is dissipated by friction in dragging the box 5 meters across the floor. Well, hopefully you remember the E-dis equation, which is the force of kinetic friction times the distance. The distance is given in the problem, but first we have to calculate the force of kinetic friction. Mu k is not the force of kinetic friction, it is the coefficient of kinetic friction. So our equation for force of kinetic friction is the coefficient of kinetic friction times the normal force. Now you can either plug the number in here, or you could go back and plug in mg, as we found a moment ago, but either way, you should get about 68.6 newtons of friction. Plug that back into our E-dis math model with a distance of 5 meters, and you get 343 joules, or to 2 sig figs, 340 joules of energy dissipated, which probably would get stored as thermal energy, heating up the box and the surface, and maybe some sound, but mostly thermal energy. So notice here you have to calculate the amount of friction to calculate the amount of E-dis. That makes E-dis actually one of the harder things to calculate. It's also a non-conservative force, which means that we need to know how far it goes. We need to know its path as it gets pulled the 5 meters. And so you'll notice that problems with friction tend to be pretty kind of boring looking problems. We drag a box across the floor. These aren't as fun as the ones we did when there was no friction, like going around a loop and going up and down hills on roller coasters and things like that, using springs, throwing things around. I mean, the friction problems are usually pretty straightforward because of the non-conservative nature of friction and requiring the distance here. Not just how you get from A to B, or sorry, not just where you start and where you end, but how you actually get from point A to point B. Now let's approach this with an energy outlook and see how fast is the box moving after it's pulled 5 meters. By the way, we could do this problem by using the force diagram to figure out a Newton's second law equation, figure out the acceleration, and then a kinematic equation to determine the velocity of the box after it's pulled the 5 meters. Since the forces are constant, the acceleration would be uniform. But we're going to approach this from an energy standpoint because we're in the energy unit. Let's put the box and the Earth in the system. If you notice clearly here, the applied force, which is being applied by something which is not part of the system, is an external force, and therefore the system is not isolated. Since the system is not isolated, the total amount of energy is going to change. It will not be conserved. Now initially, there is no EK because it's starting from rest. There is no EG, it's on the ground. And there is no EE because there are no springs or rubber bands or elastic substances. So there is no energy initially in this case. Our energy flow diagram consists of the system boundary, what's in the system, the box and the Earth. Notice whatever's applying the force here is not part of the system. But there is obviously energy flowing into our system in this case to make the box move. That, of course, is an amount of work. And work, as we learned yesterday, is the external force times the distance times the cosine of the angle in between. In this case, the external force is the applied force, which we're given in the problem. And we're pulling the box in the same direction it's moving. So remember here that theta is the angle between the external force and the displacement, which in this case would be 0. The applied force is 300 newtons. The distance is 5.0 meters. A newton times a meter is, of course, a joule. So we have a positive 1,500 joules of work done, which means we have an arrow pointing inward, which represents 1,500 joules. And notice I'm going to make this 4 boxes worth, which allows me to do this. 1,500 joules here, 1,500 joules here, but nothing initially. So finally, we are going to store 1,500 joules. Now, as we found in the previous part, 343 of those joules are stored as dissipated. There's still no elastic, no springs. There's still no EG because it's on the ground. It doesn't change heights. It's horizontal. So that means we can figure out how much kinetic energy there is. Hopefully you can see here that the kinetic energy must be equal to the work we added minus what gets stored as E-dis. That's the 1,500 minus the 343, or 1,157 joules of EK. Notice how these two columns add up to 1,500, right? The 4 total boxes. And if you remember from doing these problems before, once we know how much EK something has, we can calculate its speed by using the EK math model, 1/2 mv squared, in this case F for final. Multiply by 2, divide by m, take a square root, and you get this equation. If you need to write out the math, feel free, but here's 3 steps of algebra. Plug the numbers in, and you get your answer. The box is moving at 11 meters per second. Now that's about 25 miles per hour. So it's probably something motorized, like a car or something, that's pulling this box, not a person. It would be hard to pull this 20-kilogram box, which is about 44-pound box, at 11 meters per second.